All right, in this chapter, we don't really have a lot of reactions. We have very few of them, but one of them we do have is called the dehydration reaction, which is exactly as it sounds. It's the loss of water. That's what dehydration is. This is an opposite reaction of a reaction that we learned last chapter. Last chapter, we learned where we can take a double bond, and if you add acid and water to a double bond, you get an alcohol. All right, and remember, it goes by Markovnikov's rule. It goes on the more substituted position. Okay, well, dehydration is the opposite reaction. So you take an alcohol, you actually heat it up in acid and water, and you get a double bond. Okay, so that is actually the reaction. It's the exact opposite of what the hydration reaction is. So you take an alcohol, you add acid. You're also supposed to add heat. Now, they do not say it in here, but I do want you to add that. So heat. All right, this triangle, I don't know if you've learned this in your other classes, but that triangle implies heat. Okay, so anytime you see a triangle over an arrow, maybe because it looks like a little campfire, I don't know, but that's you're adding heat into this. And you basically eliminate water, so you can see that this H2O is what goes here, and one of the bonds from here turn into a double bond, or I think in class I talked about it as a pi bond. All right, so dehydration is an example of an elimination reaction because you're losing atoms from your molecule. All right, so here's just some real examples. If you take ethanol and add water, you can form ethylene. If you take cyclohexanol and add acid and heat, so I'm going to put heat in all these, you form cyclohexene. All right, now what happens if you do not have a symmetrical alcohol? So notice there are two possible products that you can form. You can either eliminate this water group, all right, or you can eliminate this water group. All right, and notice you'll get two different compounds. If you eliminate the water that's in red, you'll get a double bond right between here. Let's number these. 1, 2, 3, 4. You get a double bond between carbons 1 and 2. If you eliminate this side, you get a double bond between 2 and 3. Okay, so they have it in blue, and there's your 2 and 3. Notice these are not the same compounds. One's 1-butene, one is 2-butene. Okay, but it's very important that you look at the substitution of our double bond. What's our substitution? What you want to do is look at all of the groups that are directly attached to the two carbons on our double bond. So a hydrogen and a hydrogen is on carbon 1. A hydrogen and a carbon is on carbon 2. So notice this carbon has a hydrogen and a hydrogen on it. This carbon right here has a hydrogen and a carbon group. Okay, this is what's called a mono-substituted double bond. Mono-substituted. Okay, now let's look at the double bond down here. So I'm looking at this carbon here, carbon 1. Now, in reality, it's not called carbon 1. Let's actually call it carbon A, so we don't confuse it with naming, because I'm not naming right now. Okay, carbon A has a hydrogen attached to it and a carbon attached to it. So look, this carbon right here, which is attached to the double bond, has a hydrogen and a carbon. A hydrogen and a carbon. Carbon B has a hydrogen and another carbon. So since there are two carbons attached to my double bond, this is what's called a di-substituted double bond. Okay, if I had 3 carbons, let's just say I had a carbon here. I had a carbon here, a carbon here, and a carbon here, that'd be tri-substituted. If all 4 groups were carbons, they would be called tetra-substituted. All right, so notice there are 2 possible products. Well, one of these is the major product. The major product is this one right here, the more substituted. Now, we learned Markovnikov, the OH goes on the more substituted. Well, in this case, my double bond goes on the more substituted. However, it's not called the Markovnikov rule. It's called the Zaitsev's rule. Zaitsev's rule is the product that has the most alkyl groups bonded to the carbon-carbon, okay, or the more substituted. All right, so my major product is this one right here because I have 2. It's a di-substituted opposed to a mono-substituted. That's Zaitsev's rule. Okay, 4.5 is another type of reaction, but we're not going to talk about any particular reagents per se. We're just going to talk about this concept of oxidation. So in Gen Chem, you learned that oxidation, if you remember oil rig, I don't know if your teacher taught you oil rig, but I do. Oil rig stands for oxidation is loss of electrons. That's what the oil is. Oxidation is loss. And rig, reduction, is gain of electrons. Well, guess what? In organic chemistry, it's so much easier. It has nothing to do with this. So I don't even know why I brought it up. Oxidation in organic chemistry means you're adding bonds to oxygen. Okay, you're adding more bonds to oxygen. So you go from a single bond oxygen to a double bond oxygen to like maybe 2 oxygens. Okay, so you're basically increasing the number of CO bonds and you're decreasing the number of CH bonds. Okay, so here's a perfect example. Here I have an alcohol, so I have 1 bond, and the decrease of hydrogen is carbon hydrogen. So I'm looking at this carbon and I'm looking at how many hydrogens it's attached to and how many oxygens it's attached to. So I got 1 bond to oxygen and I got 1 bond to hydrogen. When I oxidize it, this is kind of the universal symbol. We're not going to talk about any particular reagents, but when you want to oxidize something, just kind of put it in parentheses. And now notice I've got 2 bonds to oxygen and I now have 0 bonds to hydrogen. I no longer have a hydrogen attached to my carbon. So I've gained an oxygen and I lost a hydrogen. That is a 1 step in oxidation. Okay, so going from a single bond oxygen to a double bond. So I go from an alcohol to a ketone or an alcohol to an aldehyde. That's a step in oxidation. Okay, I didn't realize, but they actually do talk about a reagent. It's potassium dichromate. This is one of the reagents. There are several different reagents. This is one of them. Okay, so anytime you see the symbol of O like this, most likely they're using potassium dichromate as an oxidizing reagent. Okay, you can put that on your card for when you take a quiz or an exam. You'll be able to have that on your card. Okay, so there are 2 types of oxidations. It depends if you have a primary alcohol or if you have a secondary alcohol. I believe this page is primary and the next page is going to be a secondary alcohol. All right, so primary alcohol, 1 step in oxidation stops at the aldehyde. Notice I have an aldehyde because I got rid of 1 hydrogen and I made a double bond. If I do a second step in oxidation, I can go all the way up to the carboxylic acid. Okay, so these are steps in oxidation. This is a 1 step in oxidation, and technically this would be a second step starting from here, from our alcohol. So you can go from an alcohol to an aldehyde to a carboxylic acid by adding potassium dichromate. All right, secondary alcohols can just stop at the ketone. Notice I cannot oxidize this anymore. I cannot make an ester or carboxylic acid or anything else because I don't have any more hydrogens. Remember, what does oxidation mean? Gain of oxygen, loss of hydrogen. Well, if I don't have any more hydrogen, I can't oxidize it anymore. And tertiaries, I'm sorry, I thought that was a tertiary, never mind. So here's an example of isopropanol. If you oxidize it, you can get acetone. Okay, here you go. Tertiary, you can't oxidize. Why can you not oxidize? Think about it for a second. If you said because I do not have a hydrogen, you are correct. There's no hydrogen to oxidize. Okay, so primary alcohols can go to the aldehyde or a carboxylic acid. I'll just put a shorthand. Secondaries can only go to a ketone. All right. Okay, why don't we stop right here and we will talk about the focus on the health and medicine when we come back.